Hey, good afternoon. Today we're going to talk about real-time systems. So let's get started. So we're going to review the definition of real-time systems. This shouldn't be the first time we did go through that in the introduction, but just to remind everybody, I'll do that. We're going to just look at real-time operating systems, what they need to do, and then I'll talk briefly about uniprocessor real-time scheduling and multiprocessor real-time scheduling. Okay, so the definition of real-time system is any system that has a temporal aspect in addition to its functional aspect. And when we talk about temporal aspect, we're basically talking about some time constraints. So you have to do the tasks that you have to do in a certain time period. And the key property of a real-time system is its predictability. It's not just doing the right thing, but also doing it in a predictable manner. There are, as we discussed, three types of real-time systems. There are soft real-time systems, firm real-time systems, and hard real-time systems. What distinguishes these systems from each other is how useful is the work that you do after its deadline comes. So with soft real-time systems, there is still some value in finishing the job even after the deadline. With firm real-time systems, the value of finishing a job after its deadline is zero. Basically, you can just throw it away if you didn't do it. With hard real-time systems, the value is negative. So the moment you miss a deadline, something really terrible could happen. And these are all recalls from the introduction. So we have a spectrum of real-time systems. So in this graphics that you're seeing, the left-hand side is basically a no real-time system where we have our basically usual daily systems every day. Your computer is not a real-time system, for example, although it might have some components that might have some timing constraints. But if you talk about simulations, for example, that you do for, let's say, it's actually a good connection to what we talked about scheduling. So if you're doing some simulation to study some system, it really doesn't matter how long it takes. It's gonna usually take like a few hours or a day or two. So, for those of you who have worked with machine learning, if you're training a deep learning model, that's not a real-time job because there's no actual deadline for that. So it could take a few days, it could take a few weeks, it could take a few hours, and that doesn't matter much. As you move towards the center, you're getting to the soft real-time systems. For example, if you have a cruise control in your car, that's a soft real-time system. It's not necessary to, get to a certain speed by a certain time, but it's good to do that, right? So if your goal was to get to a certain speed in 1 or 2 seconds or 10 seconds and you didn't, you still have some time, some leeway to get to that speed. Now, moving on, if you're designing electronic engines, if you're designing certain satellites, then you're basically getting close to hard real-time systems. If you make a decision after the deadline has missed, the engine could explode or your satellite could get out of the orbit and bad things could happen. So that's that. Now, let's talk about designing operating systems for real-time systems. So can we just naively deploy a general purpose operating system for a real-time system? And the answer is not really. So it's not going to be a good idea to do so. Now, the reason for that is because a general purpose operating system usually does not care about timing. So timing is not a first class citizen when you're designing operating systems in general. So let's so if you look at three categories of concepts that we talked about so far, multitasking and scheduling, interrupt management, and IPC, you can see that all of these have some randomness into them. So, you know, if you're running your task and then you run a system call, or you call a system call, your task could potentially get interrupted and preempted by another task. Let's say you want to read a file, and you don't exactly know when you're going to come back to this task or to this thread that you were running. Or if you're running your thread and all of a sudden a packet arrives, or maybe a IO that was initiated by someone else gets done, or a timer interrupt goes off, your task or your thread is going to be interrupted. And you don't really know when you're going to come back. You don't know how long it's going to take for this interrupt to be handled. And once it's handled, are you going to come back to this thread? Are you going to schedule another thread? And also with IPC and synchronization, if you're trying to lock a mutex and the mutex is already locked, you don't exactly know when it's going to be unlocked, when you're going to run again. And all of these examples show that in general purpose operating systems, usually we don't have any guarantee on the timing when it comes to executing threads. And this is bad for real-time system because it makes the system unpredictable. This randomness, this uncertainty is bad for real-time system because we have a timing constraint that we want to meet. And if there is no guarantee about the timing of certain events in the system, like system call handling or interrupt handling, then there is no predictability in executing your task. And if there is no predictability, then you cannot, avoid missing deadlines. And if you cannot avoid missing deadlines, then you're kind of screwed if you want to implement a real-time system. So let's put together all the properties that we want our system to have, or our real-time operating systems to have. We want our real-time operating system to provide predictability. So this is something that we actually don't have in general purpose operating system. We also want timeliness. We want to be able to provide timing constraints for our tasks. We want to say, I want this task to be done by this time, right? So this doesn't exist in general purpose operating system. We want fault tolerance. So this part is somehow there already. So many operating systems provide a fault tolerance. This fault tolerance piece comes usually because embedded and real-time operating systems are mostly deployed in safety critical systems, and being able to tolerate faults is a main issue when you're designing a mission critical system. You also want to design for peak load, right? you shouldn't design for average, because you want your system to work under any circumstances. So you have to always think about worst case. What happens in worst case? You shouldn't design your system for best case or for average case. And if you remember, this was the case for general purpose systems. So with general purpose system, we were just interested in average cases. Like I wanted my average throughput to be good. I wanted my average response time to be good. I wasn't thinking about, worst case throughput or worst case response time. But for real-time systems, I always have to think about worst case. Thinking about average or best case is not enough. And finally, maintainability. You want your system to be maintainable. If some changes have to be done, you don't want this to be hard. So this last one is also somehow relevant for general purpose operating systems. So if I were to just, identify the ones that are starkly different from general purpose, is this one, and this one. So these are the ones that are specific about real-time operating systems and not for general purpose operating systems. Okay, so let's talk about let's talk about the device that is going to run our real-time system or real-time operating system. So what properties or what features should the hardware provide if we really want to guarantee the properties that we just talked about? So one of the things that is very important when it comes to the microarchitecture. So in general purpose processors, the one that you have on your cell phone, the one that you have on your laptop, the one you have on your PC, I/O devices and the CPU usually share the same bus. So I will show you a better graph later on, but usually it's something like this. So you have your CPU, you have your memory system, and then you have your I/O devices. And you have a bunch of I/O devices, different I/O devices. So this is I/O controller, let's say. And let's put here something. Okay, so usually both I/O controller and the CPU have access to this shared bus to the memory. So this is almost generally correct and true for most of the processors that you have in today's systems. So, and this is fine for general purpose systems, but this could be detrimental for a real-time system. The reason is the interference on this shared bus could slow down the application that is running on the CPU. So here is an example. Let's say you want to, let's say you are doing some DMA, right? If you remember DMA, so DMA was the CPU is running something else, and in the background, the DMA engine is moving data from memory to I/O device or from an I/O device to memory. Now, if the DMA is using this bus to transfer data back and forth, and at the same time, this CPU is running a real-time task, and this real-time task also needs to access memory, then as you can see, the DMA engine requests and the task that is running on CPU, both of them are competing for the bandwidth of this memory bus. And this could slow down the real-time task that you're running, or could add some uncertainty or some randomness to the performance of the application. Therefore, it's going to make it harder to provide any guarantee on the performance of the application that is running on the CPU. So one option is to basically don't have DMAs at all, just do programmed I/O instead of doing DMA, make the CPU to transfer data back and forth between the I/O and memory. So that's one option, to just get rid of DMA altogether. This is going to be slow, right? And wasteful, because the CPU is going to be busy with doing I/O, and we saw that that's not a good idea. The other solution that you can have is to basically time share this memory bus. Make this memory bus available to only CPU at certain time slices, and only available to the I/O at certain time slices. So if the CPU is using the bus, it is sure that I/O is not using the bus. And if the I/O is using the bus, it is sure that the CPU is not using the bus. This will slow down, obviously, the CPU, but at least it provides predictability. It makes it predictable. So because I'm not competing when I'm using the bus, I can predict what happens, how long my task is going to run. So one thing that I'm going to actually pause here and emphasize is predictability doesn't mean faster. Predictability, it only means that it's predictable, even if it is slow. And predictability is good, even at the cost of not being fast, right? This is one example. So by time sharing the bus, I'm going to make it slower, but at least I'm going to make it predictable because there is no competition. The other example, as we were talking about multiprocessors, is caches. So if you remember, in general purpose processors, I have my core, my CPU core has a private cache, L1 cache, and then probably a private L2 cache, and then a shared L3 cache. Right? Now, caches are good because they're fast. So instead of the core going to memory, and this is memory, so instead of core going to memory, which is a slow, it goes to its caches to fetch data. And the closer the data is to the core, if it is in L3 or L2 or L1, the faster the memory access will be. Now, this is good if you care about average performance, because on average, you're going to speed up all your applications if you have cache. But it's bad for worst case and for predictability, because when your core issues a load or a store, it doesn't know if this load and store hit in the cache, if it hits in L1 cache, if it hits in L2 cache, if it hits in L3 cache, or if it is going to go to memory anyways. So because the data in L1, L2, and L3 caches are kind of random, they're not exactly random, but what data is in the cache depends on how applications are accessing memory. So if it is up to other applications or how the cache is implementing cache evictions, then I'm not sure for each request that I issue to memory, how long it's going to take for this request to get its answer. And this is against predictability. And as we mentioned, predictability is essential for real-time systems. So one option is to just get rid of all caches. So have no cache. This is going to be very bad for performance, but really good for predictability, because now all your requests are going to go to memory, and that is predictable. Whereas if you have caches, then some of them are going to go to the cache, some of them are not. Okay, let's move on. So I only mentioned two aspects of processor. There might be more aspects to consider. For example, NUMA is another aspect. When you have local and non-local accesses, and each one of them might have different times, then that might also add some unpredictability to your system. Cache coherency is another one. So there might be so many different aspects. The scheduling that you do given the hardware might introduce some unpredictability. So generally speaking, a processor that is designed for general purpose systems might not be a good option for real-time systems. So usually, if you have the resources, you might design your own processor for your system. So you might design your own processor for your satellite, or you might go and buy one embedded controller or embedded processor for your embedded system. So you have to keep in mind, if that option is not available to you, if you cannot design your own processor or buy your own embedded processor for your system, then you should be aware of these side effects that your processor's decision might have in predictability of your system. Now, let's switch gears and talk about software. The first aspect that I want to talk about, that I kind of like alluded to, is system calls. Now, system calls and interrupts. System calls are usually non-preemptible. So when you are handling a system call, you don't want the system call you don't want the system call handler to be interrupted. So if you're starting to, I don't know, let's say, send a request to SSD to read a file or open a file or write to a file, or you're talking to the NIC to set up a socket or something like that, you want this to happen without being interrupted. Now, this is fine for general purpose systems, but for real-time systems, this is not good, because what happens if an event happens during your system call handling process that needs your attention right away? So let's say you're setting up a socket or you're opening a file, and then your satellite changes its altitude or something, and you have to respond really fast to this change to bring it back to the orbit. Now, if your system call handler is not preemptible, then this interrupt is going to sit in the queue and not be processed. So one thing that you could do is to make your system call handling process preemptible. So this is one option. This definitely leads to some complexities in writing your system call handler, right? But if you want to design a real-time operating system, then you have to do this. Otherwise, you might miss deadlines, important deadlines, and that's not something that you want to care about. Now, when it comes to interrupt handling, it's a little bit difficult. So for certain interrupts, you really don't want your interrupts to be interrupted, right? For system call, you might want to do that. Like if you're opening a file, you could wait. You can interrupt it and then open a file. But For certain interrupt handling, you might not want to get interrupted. Now, one option, one solution is to disable all of your interrupts and only keep your timer interrupt, and let your tasks to communicate with I/O devices whenever they need by pooling. So, you know, most of the interrupts that we're talking about are coming from I/O devices or any actuator, let's say your system has, any source of creating interrupts. So what you could do is to basically communicate with them in a pooling manner. So you always pool them if you need them, and just get rid of interrupts altogether. So only keep timer interrupt in your system, and for everything else, just get rid of the interrupt altogether. So don't have interrupts in your system. So this is this addresses the issue that we had. So now that you don't have interrupts, then you don't need to deal with the issue that I said, where you're doing interrupt handling and that is leading to unpredictability. Now you're not doing any interrupt handling, so you don't have to deal with that issue. But the other good thing about this, and another good thing about this, is when you're communicating with your I/O devices or with any actuator that you have in your system, everything is predictable because the CPU is communicating with them, right? The other good thing about this is that if you want to add new devices to your system, you don't need to change anything in the kernel because the code is going to directly talk to those devices. You don't need to write a new device controller or a new interrupt handling for the new device that you're adding. So these are the three good things about this. The bad things about this is, the first one is that pooling. So you're going to do polling instead of interrupts, and polling is bad for CPU efficiency because you're going to waste CPU cycles to talk to these devices in a pooling manner. So for example, if you're waiting for a packet to come, then you can't use interrupts. You should just constantly ask your NIC, your network card, do you have a new packet? Do you have a new packet? Do you have a new packet? So you're wasting CPU cycles to just ping the network device. Whereas if you had interrupts, you could just go and do something else, and whenever there is a new packet, you will be interrupted. So that's bad. So if you want to do pooling, so you have to do busy waiting. So this is one negative. The second negative thing is, now your applications have to know a lot about different devices because they're going to talk directly to the device. So each application has to know about all the devices that they need to communicate and how they can communicate with those devices, because they're going to pool on those devices, so they have to know about them. So so we're adding a lot of complexity to our tasks by making our kernel less complex. This complexity should go somewhere, and it's going to the tasks. Okay, now that was solution number one. Solution number two is, okay, so maybe it's not a good idea to do this. So instead, let's again disable all the interrupts. So let's not have interrupts and keep the timer. But instead of asking tasks to directly talk to the I/O devices, I can create these timer activated device routines. So previously, my interrupt handlers were the ones responsible to handle any interaction with the devices. Now that I'm disabling interrupts, so I'm not going to have interrupt handlers, I can have these routines to go and pull devices, different devices, and then I can just frequently pull them. So I can set timer and every, let's say, 50 millisecond, go and pull all my devices. And then once I'm done, I go do some work, and then another 50 millisecond later, I'm going to do again. Talk to device 1, 2, 3, 4, 5, 6, see if they have anything new that I need to handle, right? So in the solution number 2, we keep this good thing because we don't have interrupt handling. So we don't need to deal with unpredictability. The system is predictable because we don't have interrupts. Now, we have also kept the execution time of communicating with devices predictable because we're still doing pooling, right? This is because we're still doing pooling with our devices. So there's a certain code that runs to communicate with the device, and we can know how long that code takes. It's not like we're doing our task and an interrupt happens and we don't know what's going to happen next. Now, the other benefit of this is that we have reduced the complexity on our tasks, right? Because communicating with devices now is implemented inside the kernel, right? So the kernel is going to communicate with all devices. So these are the good things. Now, what are the bad things? So the first bad thing is that we still are pooling. So because we're pooling, we're wasting CPU cycles. So this has not addressed from solution number 1. Now, the tasks are less complex, but the kernel is complex. So if you add a new hardware, now you have to add a new routine to your kernel and make your kernel to pull this new device as well. So kernel has become complex. And the new problem that we have added is that now that the tasks cannot directly talk to the devices, they have to talk to the devices through kernel. And that means inter-task communication probably, right? If your task wants to communicate with the device, it has to go through, for example, kernel, or it might need to communicate with other other components of your system. So we have made communication with devices more complex. So the main difference between solution number 1 and solution number 2 is in solution number 1, tasks were complex, kernel was simple. In solution number 2, tasks are simple, but the kernel is complex. In addition to that, in solution number 2, communication with the devices is more costly. Now, solution number 3 is a middle ground. So in solution number 3, we're going to allow interrupts to happen. So we're not going to disable interrupts. We're going to allow them to happen. But we're going to make the interrupt handling to be predictable. So how can we do that? How can we make interrupt handling predictable? The way you make interrupt handling predictable is through making interrupt handling minimized. So you're going to shrink the interrupt handling to the task of creating new tasks. So when interrupt happens, in general purpose operating systems, what you're going to do is you're going to handle the interrupt. Whatever interrupt has happened, you go and handle it. Now we're going to change that. We're going to let interrupts happen. When an interrupt happens, a general interrupt handling routine is invoked. And this general purpose, this interrupt handler is going to create new tasks to eventually handle the interrupt. So we're not going to handle the interrupt immediately. We're going to create a new task. Remember, this is very important. When I was talking about general purpose operating systems, I made this clear that interrupt handling is not a task. It's not a thread because it's not schedulable. Now I'm changing that. I'm saying, yes, interrupt handling is not a task. So we're going to run it immediately, but we're going to ask our interrupt handler to create new tasks to then go and handle the interrupt. So we're going to keep the interrupts enabled. We're going to reduce the interrupt handling to the least possible size. We're going to shrink the responsibility of our interrupt handlers. So what they're going to do is they're going to be activated whenever an interrupt happens, and they're going to create new tasks for us every time they handle an interrupt. Now, once the task is created, now we can schedule that task for whenever we want. So once I have the task created, I can go back to what I was doing before. So if I was running a high priority task with a deadline to come, I can just create another task to deal with the packet that was arrived or for the file that was copied, and go back to what I was doing, which was probably putting my satellite into orbit, right? So now this gets rid of busy waiting because we got rid of pooling. We're not pooling anymore. We have interrupts, so that's good. We don't need to modify kernel by much. We have this general purpose interrupt handler, which just wakes up and creates new tasks. So the kernel can be kept simple. Now, we have mitigated the communication problem because sorry, we haven't mitigated. We still have the problem with communication with the devices because now it's if the tasks are not directly talking to the device anymore. So we are creating new tasks. So we have, again, introduced inter-task communication because let's say a packet arrives, the interrupt handler creates a new task to take care of this new arrival. And then this new task at some point runs and, handles the packet, and, maybe it has to deliver this packet to another task. So now I have to do inter-task communication to communicate with my device, right? So that's a negative. And the fact that we have interrupt handler means that we're not completely, predictable. So there is some unpredictability in the system because I don't know when an interrupt is going to happen or if an interrupt is going to happen or not. And if they happen, they're going to interrupt me. Although the interrupt handling has been shortened, but interrupts could still happen, and that's random. And that means that my tasks are less predictable compared to the solution number 1 and solution number 2, because in both cases we didn't have interrupts at all. But in this case, we have interrupts. So we're losing on predictability. We have just, minimized the time that we're going to put into handling interrupts. OK, so next stop is memory management. We're going to see more on memory management in the next part of the course. But because you have already implemented memory management in Lab 1, so I can talk about dynamic memory allocation, which is what you have implemented in Lab 1, and see if that task, basically dynamic memory management, is compatible with real-time systems. So in general purpose operating systems, as we will see, so I'm going to just mention these, but we'll go to the details of each one of these bullets in the next portion of the course. So I'm going to just briefly mention. In general purpose operating systems, we usually divide the memory into pages. So we have a unit of allocation in memory, and that's page. In your implementation, we didn't have any units, so the unit was byte, and you could have multiple bytes for each region. But in general, memory is divided into pages. Now, general purpose operating systems provide address translation. So the applications, the processes that are running will create virtual address, and the virtual address has to be translated to physical address to access memory. And this address translation is stored in page tables. Again, these are topics that we will go into details in the next portion of the course. So if you miss any part, don't worry, we'll come back to it. Now, in order for us to speed up this address translation, usually one method that is used is to cache address translations in a cache that is called TLB, translation look aside buffer. So this is basically a cache of translations. So when I translate virtual address X to physical address Y, I can cache this translation, and in the future, instead of looking at my tables for this, I can look at the cache and see that, oh, I've already translated this virtual address X to physical address Y, so I can just use it instead of repeating the translation. Now, this is good for general purpose operating systems because it speeds up the average case. But like any other cache, you could hit or miss in the cache. You could find the translation in the cache, or you could miss it and you might have to do it. Now, this hit or miss is not good enough for real-time systems because it introduces unpredictability and uncertainty. So one possible solution for this is to just get rid of virtual memory. And this is very common. So many real-time operating systems do not support virtual address. So they just allow applications to use physical address. The other thing with paging is when the memory gets full, as you saw in 252, and I also mentioned, sometimes you have to swap a process to disk, right? Which is called paging. You have to put some of these pages in disk so that you have a space for other processes. Now, if you start running your process again and it needs some certain pages that are not in memory and are in the disk, then page fault happens. So page fault is a case where a certain page is stored in disk, and you have to bring it back to memory. Now this is, this happens by page fault handling, and it's very non-deterministic. So, you might experience page fault or you might not experience page fault depending on how much memory you have. And if you allow paging to happen, then you might, experience page faults, and that is basically making your system unpredictable. One solution to this is to pin your pages to memory. So tell operating system that you cannot evict these pages. You cannot swap them to disk. You have to always keep them in memory so that I don't get unpredictability. I don't get into a situation where I want my page, but the operating system has swapped it to the disk. So one solution is to just ping your pages to memory and tell operating system you're not supposed to swap them to disk. The other aspect of memory management is with dynamic memory allocation, which is unpredictable. If you look at your implementation of first fit memory allocation, you probably, whenever you get a request, you have to search your list to find a place for this request. Now, it could well be that you find a space at the beginning of your list, or you might find a space in the middle of your list, or you might find a space at the end of your list. So for any specific request, there is no guarantee that this request will be answered fast, because it could take time for you to go all the way to the end of your list, and maybe you decide that, oh, I don't have a space at all. So dynamic memory allocation introduces unpredictability, and unpredictability is not good for real-time systems. So here's an example, right? So, you allocate 3, then you allocate 4, then let's say you free P1, and then you want to now this time allocate 4 bytes. Now, you can see here, I don't have 4 bytes because, I don't have 4 bytes in contiguous memory. So I have 3 bytes here and 3 bytes here, but not 4 bytes in a consecutive or a sequence of bytes available. So this is going to be rejected, this request. Although, I had 4 bytes, but they were not contiguous. So I had to reject this request. Now, in another setting, this might actually go, right? If I had done P2 first and then P1, then P2 would be this 4 bytes. And then P1 would be these 3. And after I deallocate, then I would have 6 bytes here available. And then I could basically responds to this request, and I could satisfy this request. So this request being satisfied or not satisfied is kind of random, or it's unpredictable, depending on the sequence of requests that you get. And this is bad for real-time systems. One possible solution is to partition your memory into fixed sizes, right? Instead of allowing your users to ask for arbitrary amount of memory, like for example, in your system, tasks could ask for 4 bytes, for 10 bytes, for 20 bytes. So it's free for them to ask anything they want. But that leads to this problem that we just saw. So we can just say, no, you can't ask for arbitrary memory regions. I'm going to just give you fixed regions. So every time you ask, I'm going to give you 10 bytes, for example. So if you need 35 bytes, you have to send 4 requests. So that's an example. So that's one solution. This will definitely deal with external fragmentation, because now, everybody is asking for the same amount of bytes. So you can just divide your memory into 10 bytes, for example, and then allocate. So any request that comes, you either have 10 bytes available or you don't. So it's not going to be depending on the sequence of the other requests. The other solution is to just get rid of dynamic allocation altogether. So this is actually very common in real-time systems. They don't allow dynamic allocation. You don't have malloc, you don't have alloc or free or new. So anything that you want, you have to statically allocate it at the beginning, right? So this provides, either your code compiles and loads, or it doesn't. So you don't do it in real time when you start running. At runtime, you don't need to allocate memory. The other issue is recursion, right? So if you have a recursive function, then so let's say you have a recursive function and the termination condition depends on inputs. Then this function, the execution time of this function is unpredictable because it depends on the input. And again, predictability is key. So you don't want recursion in your real-time systems. Oh, something that I forgot about is this dynamic memory allocation is a subset of programming languages, right? So you could have programming languages that do not support, for example, dynamic memory allocation, or you could have it but not use it, you know, for your system that you're running. And here are a list of programming languages that are designed for real-time systems. Although these are mostly academic, I don't think any of these are used in practice for real-time systems. These are usually academic projects targeting real-time systems from the perspective of programming languages, like real-time Java, concurrent C, and Euclid. Okay, so next topic to discuss is scheduling. General purpose scheduling policies, as we discussed, usually target average performance. For example, you want to maximize average system throughput or minimize average response time. In real-time systems, you always want to talk about worst-case scenarios. So you want to minimize worst-case response time in your system or worst-case throughput of your system. You don't care about average. You care about worst case, because if you meet the timing for worst case, then you will definitely meet it for best case and average as well. So you always target worst case. And here is another reminder that predictability doesn't mean fast execution. Predictability means execution is predictable. I can predict how long it takes to run my task. It doesn't mean that my task is going to be slow. It doesn't mean my task is going to be fast. It doesn't talk about the speed of execution. It only talks about predictability of the execution. In many cases, as we just discussed, if you want predictability, usually you have to make your system slower. Like, for example, we had to get rid of caches. We had to get rid of, DMA, for example. We had to get rid of things here and there to make our system predictable, and getting rid of those mean probably a slower execution. Now, in the coming slides, so I'm going to talk about a few scheduling policies that are targeted for real-time systems. So all the scheduling policies that we've talked about so far, they never had any temporal aspect. There was no deadline to be met. But for real-time systems, our tasks have deadline, and we have to meet those deadlines. So we need new scheduling policies. Now, to define and talk about these new scheduling policies, I have to define some new terms that we're going to use. So the first one that we're going to talk about is the concept of jobs and tasks and periods. So real-time tasks. So we're going to talk about tasks. Real-time tasks have different types. The first type that we're going to talk about is periodic tasks. So these tasks have a set of jobs that arrive at fixed periods. So if task A is periodic, this means that task A has a set of jobs that come at certain periods. So I have real-time task. A task has a set of jobs, and these jobs arrive at certain period. Now, each job has a worst case execution time. So we're assuming that we know how long each job is going to take to finish. Now, this assumption was kind of weird in general purpose systems because there were so many randomness. But now that we're targeting real-time systems, as we talked so far, we want the system to be predictable. So it's not a big assumption to know how long each task takes, because we have made our multiprocessor or our processor predictable. We have made our operating system predictable. So it's not far-fetched to assume that we know worst case execution time of our jobs. So from now on, I'm going to assume that we know the execution time of each job. So that's given to us. And we're going to assume that jobs have hard deadlines. So, you know, they're going to come at certain periods, and when they come, they have to be finished by a certain time. So basically, I have a deadline. This is a relative deadline. Well, and it has to be less than the period, right? So let's say if my period is every 10 seconds, so this is time. Let's say at time 0, I get one job. At time 10, I get another job. And let's say the execution time of my job, if execution time of my job is more than 10, then I'm screwed, right? Because I'm going to, you know, run this task and this job, and before I finish it, another one comes, and before I finish that one, another one comes. So I'm going to have a lot of jobs that I haven't finished. So the execution time is often less than the period. So the deadline should also be less than period, right? Usually this example, let's say I get a job every 10 seconds, and each one of them runs for 2, and let's say the deadline is 3. So I have to finish them after 3 seconds after their arrival. So we're gonna assume that the deadline is less than the period, but then usually from now on we're gonna just assume that the deadline is equal to period. So whenever, you know, either I tell you what the deadline is. If I don't tell you the deadline, then assume that the deadline is equal to the period. So in this case that I have in this example, I said the deadline is 3, so the relative deadline is 3. Hadn't I said that, you should have assumed that the deadline is basically this 10. So I have to be done with this task 10 seconds after its arrival. Okay, the utilization of a task is the ratio of the execution time of the task divided by the period of the task. So if I'm getting one job every 10 seconds, and if my job execution time is 2 seconds, then the utilization of my job is 2 to 10, which is this. So this is my utilization. Utilization is the execution time divided by period. Now, if your utilization is 1, this means that your execution time equals your deadline. And your deadline in this case, let's say if your deadline is equal to your period, it means that you have to just constantly run this task. If you have a CPU, your CPU should always run this task, because whenever it comes, it's going to take its period to finish, and by the time that it finishes, another one comes, and because the other one deadline is its period, you have to immediately start running it, because if you delay running it, you're going to miss the deadline. So you're going to run the next one and the next one and the next one. So you have to dedicate a single CPU to this task. So if you have a task with utilization 1, it means that this task requires a single CPU all the time, and it's going to utilize the CPU 100% of the time. So that's that. So this is periodic tasks. Not all real-time tasks are periodic. You might have aperiodic tasks. So aperiodic tasks don't have a fixed period. So this means that they come, the jobs come randomly, right? They don't have any period. Then you have and they don't have a deadline. So for aperiodic, there is no period and there is no deadline. For sporadic tasks, they could come at any time, so the arrival is random, but they do have a deadline. So when they come, they have to finish after a certain amount of time. So these are the 3 types: periodic, aperiodic, and sporadic. So these are the 3 types. Now, when you're talking about real-time tasks, they might be independent or they might be interdependent. So for most of the things that we're going to talk about, we're going to assume that tasks are independent. So task 1 and task 2, they don't have any dependency. In reality, that's not always the case. So you might get tasks that depend on each other, right? But for simplicity, we're going to assume that tasks are independent. Then, sorry. The other thing is preemptible versus a non-preemptible. We're going to assume that tasks are preemptible. So again, that's not always the case. You might have systems that are non-preemptible. So if you start a task, you have to finish it. But again, for simplicity, we're going to assume that we can preempt tasks at any time that we want. Okay, so let's talk about terminology of real-time scheduling. The first class of scheduling policies is called a static scheduling. So in a static scheduling, the priority of each task does not change over time. So each task is assigned a priority, and that priority is fixed, and it's not going to change over time. An example is rate monotonic. So we'll talk about RM in the future slides. I'm just putting the name out, and then we'll see the details. Another type of a scheduling policy is dynamic scheduling. So with dynamic scheduling, we're going to give fixed priority to jobs, not to tasks. So again, I remind everyone that we had the hierarchy was tasks, and then each task has jobs. With a static scheduling, each task gets a fixed priority, and well, all the jobs inside that for that task basically have the same priority as that task. With dynamic scheduling, we're going to assign different priorities to different jobs, but when we assign priority to a job, it's not going to change over time. So each job gets its priority, and that's fixed. But different jobs for the same task could have different priorities. The third class is fully dynamic scheduling. In fully dynamic scheduling, we're going to assign priority to jobs, but that could change over time. So the priority of a job could change over time. So your job could have high priority and then later on become low priority, or it might have low priority and then later on it becomes high priority. And an example for dynamic one is earliest deadline first, and for fully dynamic scheduling is least laxity or laxity first. So we're going to actually talk about all three scheduling policy in the coming slides. So now a scheduling policy is called to be feasible if, pardon me, check for questions so far. Okay, so a scheduling policy is feasible if it can meet all the deadlines for all the tasks. So that's that. Now a task set, basically a workload. Let's say I give you a set of tasks with certain period, with certain execution time, and with certain deadline. So this becomes your workload. Now I say this task set is schedulable under this scheduling class if there exists a scheduling algorithm in this class that could produce a feasible schedule for this workload. So if I say for workload X, a static scheduling is, sorry, if I say this task set X is schedulable under a static scheduling class, it means that there is one static scheduling algorithm that can produce a feasible schedule for this task. Finally, a scheduling algorithm from a class is called optimal in that class if it produces feasible schedule for any schedulable task set. So we're going to see examples of this. So if you kind of didn't get this, wait, we're going to come back to them. I'm going to repeat one more time. So a single scheduling algorithm or a single schedule, sorry, is said to be feasible if all the deadlines are met. Now, a set is called a schedulable under a scheduling class if there is a scheduling algorithm in that class, like A in C, that produces a feasible schedule. And finally, we say a scheduling algorithm A is optimal with respect to this class if this scheduling algorithm can produce feasible schedules for any schedulable task set under C. Okay, now let's see how general purpose scheduling policies will fail in real-time systems. And by failing, I mean they cannot guarantee deadlines are met. They cannot produce a feasible schedule. So let's focus on round robin. Let's assume that I have 3 tasks. So I guess I should have emphasized the notation. So this notation that you see here, T1, then there is a pair 2, 1. So the first one is the period and the deadline. So it's P and D. And the second one is the execution time. So this means that task 1 is periodic. So it's going to have one job every 2 seconds. And each job is going to take 1 second. Okay, so let's mark the arrivals. For T1, we're going to have a new job every 2 seconds. For task 2, we're going to have a new job every 5 seconds, basically the period. And for task 3, we're going to have a new job every 10 seconds. So these are the arrivals. So at these points, we're going to get a new job. Okay, now let's apply round robin to this and see how round robin will schedule these tasks. So let's assume that T1, T2, and T3, all of them get a new job at time 0. So all of them will get one job at this time. So they all have an arrival. And let's say they're in the queue with the same order. So T1 is the head of the queue, then T2, and then T3. And now let's run round robin. So round robin, and let's assume that the time quantum is 1, so 1 second. So round robin is going to run the T1 job first. Then it's going to run T2 job second. Then it's going to run T3 job. So it's going to run one of the. So this job is going to take for 3 seconds, but because the time quantum is 1, I'm going to just run 1 second of this job and then context switch. Now, who else now is in the queue? The T1 job has arrived. Now T2 is done because it only had one job, and that job only took 1 second. So T2 doesn't have any jobs in the system. So if I look at the queue, I have T1. So I'm going to go and run T1. Now at this point, I don't have anything from T2, so I'm going to go back to T3. So I'm going to run T3. Now at this time, at the end of this time, I have received 1 task from T1 and 1 task from T2. So if I look at my queue, T1 is at the head of the queue, and then T2. And now that I'm done with T3, I'm going to put T3 at the back of the queue. So I'm going to go and execute the T1, and then I'm going to run the T2. And finally, I'm going to come back and run T3. At this point, T3 is done. So I can go back to T1. But as you can see, T1 had a new job here, but I missed it because instead of running T1, I went and ran T2, and after that I ran T3 because that was the order in round robin. And now that I'm coming back to T1, T1 has already missed its deadline. Oh, this should be T1. So job 4 of task 1 missed its deadline. Okay, so this is an example to show you that round robin or any other general purpose allocation, or sorry, a scheduling mechanism is not going to work because they just ignore deadlines, right? Round robin doesn't care about deadlines. It just cares about the order of tasks in the queue. And it's going to miss the deadline, as you just saw in this example. Okay, so now let's talk about scheduling policies that are actually designed for a real-time system. The first one that we're going to see is rate monotonic scheduling. What is rate monotonic scheduling? So rate monotonic scheduling is going to assign a priority to each task. Now, the priority that each task gets is depends on the execution time of the task. Sorry, it depends on the period of the task. So the shorter the period of the task is, the higher its priority becomes. So, you know, if you have a task that has short period, you're going to give it higher priority. The reason for this, or the intuition behind this, is that if my period is short, this means that my deadline is also short. So my deadline is going to come fast. Therefore, I should have higher priority so that I can meet my deadline. So that's the idea. So rate monotonic is a static scheduling policy. The reason that it's a static is because each task gets priority, right? And this priority doesn't change because the priority of each task is the inverse of its period. So the shorter my period is, the higher my priority becomes. And it's not going to change over time. So it's a static allocation. Now, it's optimal with respect to a static schedulers. So what does this mean? It means that if there is a task set, if there is a workload that is schedulable by any other static scheduler, so there might be some other static schedulers, if they can produce a feasible schedule for this task set, then RM can do the same. So that's the notion of optimality that we're talking about. So if any other scheduling policy in this class can schedule this workload, then RM can also schedule this workload. That means that RM is optimal. Let's look at the same example that we just ran for round robin and see how RM deal with it. So in this example that you're seeing, task 1 period is 2, task 2's period is 5, and task 3's period is 10. This means that T1 is going to get the highest priority because it has the shortest time, it has the shortest period. Task 2 is going to be the middle priority, and task 3 is going to be the lowest priority. Now, again, let's look at the arrivals. So these are the arrivals. Let's assume that everybody gets 1 arrival at time 0. Now, at this time, I have 3 tasks in my queue. Which one has the highest priority? Well, T1 has the highest priority. So I'm going to run T1 first, then T2. Now, at this time, another job from T1 comes. So now I have 2 jobs in my queue, a job from T1 and a job from T3. Because T1 has the lowest, has a shorter period, it has a higher priority. So I'm going to now run the job from T1 because it has higher priority. And then I'm going to go run T3. Again, at this point, I get a new job from T1 and it has higher priority. So I'm going to run that one. Now, at time 5, I get a T2 job. So I have a T2 job and I have a T3 job to execute. Which one has higher priority? Well, T2 has higher priority. So I'm going to run that. Then I get a job from T1, so I'm going to run T1. And at this point, I don't have any job from T1. I don't have any job from T2, so I can go and run T3. So I run T3, and so on and so forth. And as you can see, RM is able to produce a feasible a scheduling policy for this workload. And I only needed to show you all the way to time 10, because after this, it repeats itself, right? Because 10 is the common multiplier of 2, 5, and 10, right? So if I do the scheduling for all the way to time 10, then it will just repeat itself. Okay, so I guess I'm going to stop here. I'm over time. So on Tuesday, so next Tuesday, we'll hopefully go through the rest of the lecture. So I sent an email to the class with regard to the final. So please make sure that you participate and you participate in the quiz. It's not a quiz, it's a poll. Okay, so thank you for sticking around, and thank you for those of you who are watching the lecture. Stay safe. I'll talk to you on Tuesday. Bye.